You're looking inside, and I don't mean finding yourself in some kind of spiritual sense. I mean literally looking inside at the absolute chemical chaos that is currently keeping you alive.
It really is chaos, isn't it? But it's a very, very tightly controlled chaos.
Controlled is the perfect word. I was reading through our source material for this, chapter 65, Secretory Functions of the Alimentary Tract.
Yeah.
And I have to admit, I went into it thinking, okay, digestion. It's spit and stomach acid. How complex can it possibly be?
And then you saw the numbers.
Then I saw the numbers. There is one statistic right at the top of the chapter that just, I mean, it smacked me in the face.
Right.
The alimentary tract, so, the tube running from your mouth all the way down to your colon, it secretes about 6.7 liters of fluid every single day.
It is a staggering amount when you really stop and think about it.
6.7 liters. That is, what, almost 7 of those big Nalgene water bottles?
Mm-hmm.
Every single day. We were just walking around, answering emails, driving our cars, while our body is silently pumping out and then mixing and then reabsorbing 7 liters of some of the most, frankly, dangerous chemicals in nature.
And that's really the mission of today's deep dive, right? We need to understand not just that this happens, but how it happens. Because look, if that 6.7 liters was just water, we'd be fine, but it's not water.
Right. If it were water, we wouldn't digest anything. It'd just be an internal car wash.
Exactly. This fluid is a cocktail. It's hydrochloric acid, it's bicarbonate, potassium, proteolytic enzymes, detergents, mucus. I mean, it is designed to dissolve solid matter, a steak, fibrous vegetables, fats, while somehow, and this is the magic, somehow not dissolving the body that produced it.
That is the tension that just drives this entire chapter, isn't it? We are essentially a soft, fleshy bag containing a mixture that can literally melt meat. So the question is, how do we not digest ourselves?
And the answer is just incredibly complex. It involves these intricate neural networks, hormonal triggers, and some very, very specific cellular machinery.
So here's the plan for you listening. We're going to take a tour. We are starting at the factory floor, the cellular level, to see how a gland actually works. Then we are going to travel the whole route: mouth, stomach, pancreas, liver, and then finally the colon. We're going to look at the specific, let's call it the secret sauce, that each organ adds to the mix.
And broadly speaking, as we go through this, you should keep two main goals in mind. Everything we're about to talk about serves one of two masters: digestion or protection.
Digestion is the offense, protection is the defense.
Precisely. You need enzymes to break food down, that's your digestion. But then you need this layer of mucus and buffers to stop those very same enzymes from eating the gut wall. That's protection. It's a constant high-stakes tug-of-war.
Okay, so let's put on our hard hats and step onto the factory floor. Before we even get to the specific organs, the source material lays out these general principles of secretion. It turns out, whether it's a salivary gland in your cheek or, the pancreas deep in your abdomen, the basic machinery is surprisingly similar.
Well, biology loves to reuse a good design. Why reinvent the wheel when you have a cell that works perfectly?
But it's not just one type of factory, is it? There's a hierarchy here. The chapter breaks them down by complexity.
Right. Think of it like manufacturing. At the simplest level, you have let's call them the cottage industry workers. These are the single-cell mucus glands, often called goblet cells.
Goblet cells, that's a great name.
It's because they look like a wine goblet under a microscope, sort of fat at the bottom and narrow at the top. And these guys are lone wolves. They just sit on the surface of the gut epithelium. They don't need a complex neural network to tell them what to do.
So they're independent contractors.
Totally. If a piece of rough food hits them or there's some kind of chemical irritant, they respond directly to that local irritation. They just extrude mucus right there on the spot.
So it's a localized SWAT team. Irritation here, deploy slime.
Exactly. It is a direct, immediate response system. Then you step up in complexity to the pits. These are invaginations, basically little caves or depressions in the gut wall. In the small intestine, we call them the crypts of Lieberkühn.
Crypts of Lieberkühn sounds like a level in a dungeon crawler video game. You must survive the crypts of Lieberkühn to retrieve the golden enzyme.
It really does, doesn't it? But they are actually these incredible water and electrolyte factories, which we'll get to. Then in the stomach, you have deep tubular glands. These are even more specialized. Think of them as long, narrow test tubes lined with different cells that produce things like acid and pepsin.
And finally, we get to the heavy industry.
The complex compound glands. These are the big ones. The salivary glands, the pancreas, the liver. And what's interesting is that these technically lie outside the alimentary tract itself. They are massive factories that produce secretions in these structures called acini.
Acini. like ACINI.
Exactly. You can think of them like clusters of grapes. And they produce this juice and then feed it into a complex system of ducts that eventually empties into the gut.
Okay, so we have the factory layout. Now I want to zoom in even further. I want to look at a single cell because figure 65.1 in the text breaks this down, and it really does look like an assembly line. How does a single cell actually build an enzyme or a protein for secretion?
It is surprisingly industrial, and it all starts with logistics. The raw materials, so your amino acids, glucose, fats, they arrive at the base of the cell, delivered by the capillaries.
So the blood delivers the parts to the back door of the factory.
Right. But you can't run a factory without power. So the mitochondria, the cell's power plants, take those nutrients and use oxidative energy to churn out ATP, adenosine triphosphate, the energy currency of the cell, and secretion is incredibly energy expensive.
Okay, so we have parts, we have power. Where is the actual assembly line?
That would be the endoplasmic reticulum and the Golgi complex. The ribosomes on the endoplasmic reticulum are the workers. They get the blueprints from the nucleus and stitch the amino acids together to form proteins.
And then these newly made proteins move to the Golgi.
Yes. The protein travels through the tubules of the endoplasmic reticulum to the Golgi complex. And this transit isn't instant. The text says it takes about 20 minutes. Inside the Golgi, the materials are modified, they're concentrated, and then they're packaged into what are called secretory vesicles.
These vesicles are like the shipping containers, the final product, boxed up and ready to go.
Exactly. And they are stored at the apical end of the cell. That's the top end, the one facing the gland's opening. They just sit there, hundreds or thousands of them waiting.
And this was the part that kind of confused me initially. They don't just trickle out as they're made. They wait for a specific signal.
Usually, yes. They wait for a signal. You can think of it as just-in-time manufacturing for the body. You don't want digestive enzymes floating around when there is no food. That would be incredibly wasteful and potentially very dangerous.
So what pulls the trigger? What's the signal to ship the product?
It's usually a neural or a hormonal signal. The hormone or neurotransmitter binds to a receptor on the cell's surface, and this kicks off a whole signaling cascade inside the cell that does one very specific, very important thing. It increases the cell membrane's permeability to calcium ions.
Calcium. I feel like every time we do a biology deep dive, calcium is the trigger man. It's always the key.
It almost always is. Calcium rushes into the cell from the extracellular fluid, and that sudden influx of calcium is the signal. It causes the vesicles to fuse with the cell membrane. The membrane breaks open at that point, and the content bursts out into the gland's lumen. We call this process exocytosis.
So it's a bursting mechanism. The cell doesn't just open a little door, it literally spits out the cargo.
Precisely. And in many cases, water and electrolytes will follow the organic material, almost as if to wash it out of the gland and into the duct system.
Now, before we leave these general principles, we have to talk about mucus. The text spends a surprising amount of time on mucus, and I think for most of us, we just think of it as, well, gross, or just something you blow out of your nose when you have a cold.
It gets a really bad rap. But without mucus, the chemical industry inside us would burn the factory down in a matter of hours. It's not just slime. It's a highly engineered tactical material.
The source material lists 6 essential properties. And looking at them together, it's basically a biological super lubricant.
It is, and it's worth breaking them down because the chemistry is fascinating. First, it has adherence. It sticks tightly to food particles. If you didn't have this property, food wouldn't slide smoothly. It would scrape and abrade the lining of your gut.
Ouch. Yeah, that sounds terrible.
Second is body. This means it's thick enough to coat the gut wall in a substantial layer, preventing any actual physical contact between the food and the mucosa itself. It's a shock absorber and a physical shield.
And then the third one, this one seemed like a contradiction to me at first. It's listed as low resistance. How can it stick to things but also have low resistance?
That's the magic of glycoproteins, the main component of mucus. They are long-chain molecules that can entangle with food, giving it adherence. But the layer facing the gut wall is organized in a way that it slides with minimal friction. So it's sticky on the inside, facing the food, but incredibly slippery on the outside, facing the gut wall.
That is seriously high-tech stuff. It sounds like something NASA would have to invent for a spaceship.
Nature definitely beat them to it. The fourth property is adhesion. It helps bind fecal particles together in the colon, which is more important than it sounds. Fifth is its resistance to digestion, and this is critical. The enzymes that are designed to digest the steak you ate do not easily digest the glycoproteins and mucus.
So it's a shield that the weapons can't penetrate.
Exactly. And the sixth one, this was the science word you probably like, amphoteric properties. Ah, yes, amphoteric. This just means it can act as both an acid and a base. Mucus contains buffers, usually bicarbonate ions, that can neutralize small amounts of acid, but it also has acidic radicals that can buffer bases. So it's not just a physical shield, it's an active chemical shield as well.
Wow. So as a chemical buffer, a lubricant, a glue, and a shield all in one package.
All in one. Without mucus, the source is clear. You would have massive excoriation and self-digestion within hours.
Okay, keeping that incredible shield in mind, let's start the journey. We're at the entrance, the mouth.
Where it all begins, the first stop.
We have the salivary glands. The text names the big three: parotid, submandibular, and sublingual. And it says we produce between 800 and 1,500 milliliters of saliva a day. The average is about a liter. That's a whole liter of spit.
It's a lot of fluid, and it's not all the same. It's a mixture of two basic types of secretion. First, you have the seroous secretion, which is very watery and contains an enzyme called chyalin.
Chyalin. That's a digestive enzyme, right?
Yes, it's an alpha amylase. Its job is to start digesting starches right there in your mouth. If you chew a piece of bread for a long time, you might notice it starts to taste a little sweet. That's chyalin breaking the complex starch bonds down into simpler sugars.
And the second type is the mucus secretion.
Right, which contains a glycoprotein called mucin. And that, of course, is for lubrication, helping you form the food into a bolus that you can swallow. The different glands specialize. The parotid glands, the ones back by your ears, are almost entirely serous. They provide that watery enzyme wash.
And the other ones?
The submandibular and sublingual are mixed glands. They produce both. And then the tiny buccal glands in your cheeks are almost purely mucus.
Now, I really want to deep dive into figure 65 too, because this was where the chemistry got pretty dense for me. The text makes a huge point that saliva isn't just filtered blood plasma. The ion concentrations are totally different.
Right. This is a classic example of how the body actively modifies fluids. Saliva secretion happens in two distinct stages. Stage 1 happens in the acini, those blind ends of the glands, the grape-like clusters. Here, the cells produce the enzymes and secrete a fluid that is chemically very similar to the extracellular fluid that bathes all our cells. It's isotonic.
So at this point, the salt levels, the sodium and chloride, are basically the same as the rest of the body.
Correct. But then comes stage 2. This primary secretion flows down the salivary ducts. And the cells that line these ducts are not just passive pipes. They are active workers. They fundamentally modify the fluid as it passes by.
What are they doing to it? What's the modification?
They are actively running pumps. First, they pull sodium ions, Na+, out of the saliva and pump them back into the blood. In exchange, to balance the electricity, they actively secrete potassium ions, K+, into the saliva.
Okay, so it's a trade. Sodium out, potassium in.
Yes, but, and this is the key part, they pull much more sodium out than they put potassium in. This creates an electrical potential, a charge of about negative 70 millivolts inside the duct. This negativity then pulls the negatively charged chloride ions, Cl, out of the saliva passively. They just follow the electrical gradient created by the sodium removal.
Okay, so sodium and chloride, which is basically table salt, are being actively and passively removed from the saliva.
Exactly. And at the same time, the epithelium of the duct secretes bicarbonate ions into the saliva.
So, after all that chemistry, by the time it reaches your mouth, what do we have? What's the final product?
You have a fluid that is hypotonic, meaning it has a much lower salt concentration than your blood, but it's extremely rich in potassium and bicarbonate.
Why? I mean, what's the purpose of having low salt, high potassium spit?
Well, the low salt content enhances taste sensitivity. If your saliva was already salty, you wouldn't be able to taste the salt in your food as effectively. But there is a fascinating nuance here that the text calls the flow rate factor.
Oh, I caught this. This is really cool. It's all about speed, right?
It's all about time. The modification process, pulling out sodium, putting in potassium, it takes time. Under resting conditions, when you're just sitting there, the flow is slow, so the duct workers have plenty of time to modify the fluid. The saliva is very hypotonic. But what if you stimulate the glands intensely?
Like when you're about to vomit or you bite into a super sour lemon.
Exactly. The flow of primary secretion becomes a torrent. It rushes through the ducts so fast that the workers can't keep up with the modification. there just isn't enough time.
So the factory assembly line is moving too quickly for them to pick off all the sodium ions as they go by.
Precisely. So during periods of high salivation, the final composition of saliva becomes much more like the primary excretion. It's more isotonic, with much higher concentrations of sodium and chloride.
That is such a cool mechanical detail. It's not just on or off, it's a gradient based on flow. Now, besides just starting starch digestion, saliva is basically our mouth cleaning crew.
It is absolutely vital for oral hygiene. The mouth is, it's warm, it's wet, it's full of food particles. It's a paradise for bacteria. We should theoretically have raging infections and cavities constantly.
So why don't we?
Well, first, the flow of saliva itself physically washes away pathogenic bacteria and the food particles they would otherwise feed on, but it's also active chemical warfare. Saliva contains thiocyanate ions.
Thiocyanate, that sounds pretty poisonous.
To bacteria, it is. These ions, along with proteolytic enzymes like lysozyme, directly attack bacteria. Lysozyme literally digests the cell walls of certain bacteria, causing them to rupture. And the thiocyanate ions can actually enter the bacteria and become bactericidal. They kill them from the inside out.
The text also mentions antibodies in there, too.
Yes, specific protein antibodies that can destroy oral bacteria, and they are particularly important in preventing dental caries, what we call cavities. The text makes a sobering point that in patients with xerostomia, a condition where they produce almost no saliva, their gums can become ulcerated and their teeth can literally rot away within months.
That's terrifying. It really shows that saliva isn't just water. It's a constant antibiotic rinse for your entire mouth.
Absolutely. It's our first line of defense.
Let's just touch on regulation before we swallow. I mean, I know just thinking about lemons or a good meal makes me salivative.
Oh, that's the nervous regulation network. It's
Good.
primarily controlled by the salivatory nuclei, which are located in the brainstem. And you're right, taste is a huge trigger, especially sour taste from acids. Acidic foods trigger a massive watery saliva production to dilute and buffer the acid.
And the text mentioned a circulatory connection here that I found really fascinating. It's about the blood supply to the glands.
This is a beautiful piece of integrated biochemistry. When the glands are triggered to work, they need more raw materials, right? So they need more blood flow. The parasympathetic nerves that trigger salivation also cause the gland cells to release an enzyme called kallikrein. Kallikrein acts on a protein that's already in the blood and splits off a small peptide called bradykinin. And bradykinin is an extremely potent vasodilator. It forces the blood vessels supplying the gland to open wide.
So the signal to make spit simultaneously sends a signal to send more blood. It's one signal with two effects.
It guarantees that the supply line opens up exactly when the factory ramps up production. It's just beautifully efficient design.
Okay, let's swallow. The food bolus goes down the esophagus.
The esophagus is mostly a transit tube. It's a muscular chute. Its secretions are entirely mucus. It's all about lubrication to make sure that food gets to the stomach without friction.
But there are some special glands at the very top and the very bottom.
Right. At the gastric enso, where the esophagus meets the stomach, there are these compound mucus glands that are crucial. They produce an extra thick, alkaline mucus to protect the esophageal wall from acid reflux. If that barrier fails, the stomach acid can splash up and eat away at the esophageal lining. That's what heartburn is. And if it's chronic, it leads to ulcers.
Which brings us to the main event, the stomach, the acid bath.
This is where the chemistry gets really, really intense.
The anatomy here, in terms of glands, is basically divided into two main sections, right?
Yes. The proximal 80%, that's the body and the fundus of the stomach, contains what are called the oxyntic glands. Oxyntic just means acid forming. And the distal 20%, the antrum, near the exit, contains the pyloric glands.
So the top part of the stomach makes the acid, and the bottom part makes the what exactly?
The pyloric glands make a lot of mucus, mostly for protection, but they also produce the incredibly important hormone gastrin, which, as we'll see, controls the whole process.
Let's focus on those oxyntic glands first, because this is where the magic happens. They have three main cell types that the text points out.
Right. First, you have the mucous neck cells. As the name suggests, they create mucus, but they're also important stem cells that replicate to replace the stomach lining, which has a very high turnover. Second, you have the peptic cells, which are also called Schake cells. These secrete pepsinogen. And third, you have the parietal or oxyntic cells. These are the real stars of the show. They secrete two things: hydrochloric acid, HCl, and intrinsic factor.
I really want to deep dive into this acid mechanism using figure 65-6 from the text, because making concentrated acid seems incredibly dangerous for a biological cell. I mean, a cell is made of protein and fat, acid destroys protein and fat. So how does it make something that should, by all rights, kill it?
It requires a very specialized, very powerful pump and a whole lot of energy. The parietal cell membrane contains the hydrogen-potassium ATPase pump. In medicine, we usually just call it the proton pump.
Okay, so walk us through the physics here. How does it work?
Inside the cell, water, H2, dissociates into a hydrogen ion, which is a proton, and a hydroxide ion. The pump, this ATPase, grabs that hydrogen ion and uses the energy from ATP to actively force it out of the cell and into the stomach lumen. But it's an exchange pump. For every hydrogen it forces out, it brings a potassium ion in.
So it is literally pumping hydrogen out. Okay, but that's just H plus on. Where does the chloride come from to make HCl, hydrochloric acid?
That's the other half of the equation. The chloride is also actively pumped out of the cell into the lumen through its own separate channel. So once they're outside the cell, inside the stomach gland, the hydrogen and the chloride ions meet and form HCl.
And the text says the pH of this secretion can be as low as 0.8.
0.8. That is extremely, extremely acidic. We're talking battery acid territory. To give you some context, the hydrogen ion concentration in this secretion is about 3 million times higher than the concentration in your arterial blood.
3 million times.
3 million times. To pump hydrogen ions against that kind of an incredible concentration gradient requires a massive amount of energy. The text notes that making 1 liter of this gastric juice requires more than 1,500 calories of energy.
That could explain why we feel tired after a huge meal, right?
Mm-hmm.
The acid factory is drawing all the power from the grid.
In a metabolic sense, yes, absolutely. Parietal cells are absolutely packed with mitochondria just to generate that amount of ATP. They are the power users of the gut.
But here's the burning question. If the pH in the gland is 0.8, why doesn't the acid just leak back into the cell and destroy it? Or leak between the cells and destroy the stomach wall?
That's where the gastric barrier comes in. The cells of the stomach lining are joined together by what are called very tight junctions. They form an incredibly effective seal that prevents the acid from leaking back into the mucosa. However, the text gives a stark warning that certain substances, like alcohol or aspirin, can disrupt this barrier.
So a few drinks or some aspirin can actually break the seal.
Yes, they can damage the lipid membrane of the cells and weaken those tight junctions. If the barrier is breached, acid leaks back into the mucosa, causing cell damage and digesting the stomach wall from the inside. That's what causes the burning pain of gastritis.
Okay, so that's the acid. But the parietal cells make two things. What's the other one? Intrinsic factor.
Intrinsic factor is vital. Its sole job is to bind to vitamin B12 from your food. This combination is necessary for B12 to be absorbed later on, way down in the ileum.
What happens if you don't have it, if your parietal cells are damaged?
You develop a condition called pernicious anemia. This often happens in people with chronic gastritis, where the acid-producing cells atrophy and are destroyed. No parietal cells means no intrinsic factor. No intrinsic factor means you can't absorb vitamin B12. And without B12, your bone marrow cannot properly mature new red blood cells.
Wow, so the health of your blood is tied directly to the health of your stomach lining.
Absolutely. It's a perfect reminder of how interconnected all these systems really are.
And we also have pepsinogen from the chief cells.
Right. Pepsinogen is an enzyme precursor. When it is first secreted by the peptic, or chief, cells, it's completely inactive. It does absolutely nothing.
It's a dud.
It's a critical safety feature. You do not want an active protein-digesting enzyme inside the very cell that made it out of protein. But as soon as that pepsinogen hits the acid in the stomach,
boom,
activation. Contact with hydrochloric acid instantly cleaves a part of the molecule off and turns it into its active form, pepsin. And pepsin is a powerful proteolytic enzyme. It begins the digestion of proteins, like in meat, and crucially, it only works in a highly acidic environment. Its optimum pH is between 1.8 and 3.5. If the pH rises above 5, it loses almost all of its activity.
So the acid is the on switch that activates the protein digestion. They have to work as a team.
Perfect partnership.
Let's talk about how this whole acid bath gets turned on. The text mentions a trio of signals that stimulate secretion.
The three musketeers of acid secretion: acetylcholine, gastrin, and histamine.
Acetylcholine, that's the nerve signal, right?
Yes, it's released from the vagus nerve. It's a general stimulant. It stimulates all the cell types, the mucus cells, the pepsinogen cells, and the acid-producing cells.
Okay, then there's gastrin.
Gastrin is a hormone. It's released by specialized G cells in the pyloric glands at the bottom of the stomach, usually when they detect the presence of protein in the food you've eaten. Gastrin then gets released into the blood.
And where does it go?
It travels through the bloodstream and primarily targets a special cell type called the enterochromaffin-like cell, or ECL cell.
ECL cells. These sound like the middlemen.
They are absolutely crucial. They lie deep in the oxyntic glands, right next to the parietal cells. When gastrin from the blood hits the ECL cells, it causes them to release histamine,
Histamine, like the stuff involved in an allergic reaction.
the very same molecule, but here it's acting as a local messenger, a paracrine signal. The histamine diffuses over the short distance to the nearby parietal cells and acts directly on them to stimulate massive acid production. It's the most powerful signal for acid.
So the chain of command is protein in the food triggers gastrin release, gastrin travels in the blood and triggers the ECL cells. The ECL cells release histamine, and the histamine is the direct, powerful signal for the parietal cells to pump out acid.
Exactly. And that, by the way, is why some of the most effective drugs for heartburn and ulcers like Zantac or Tegamet work. They are H2 blockers. They block that specific histamine receptor on the parietal cell.
Okay. Connecting the dots. Now, the text breaks down gastric secretion into phases. It's not just an on-off switch when food hits the stomach.
No, it's much more elegant. It actually starts before you even take a bite. Phase 1 is the cephalic phase. This accounts for about 30% of the acid secretion for a meal. It happens entirely via the vagus nerve when you just smell food, see food, or even think about food.
So my stomach is probably making a little bit of acid right now
Right.
just because we're talking about this so intensely.
It's very likely yes. Your brain is anticipating food. Then phase 2 is the gastric phase. This is when food is actually in the stomach. This triggers local nervous reflexes and, most importantly, that gastrin mechanism we just discussed. This phase accounts for about 60% of the total secretion.
And what about phase 3?
The intestinal phase. This is a much smaller component, only about 10%. It happens when food, now called chyme, begins to move into the duodenum, the first part of the small intestine. It causes a small amount of continued gastric secretion.
But the intestine also has a braking mechanism, right? It needs to be able to tell the stomach to stop sending acid its way.
It absolutely has to. The small intestine can only handle so much acidic chyme at once. It gets overloaded, or if the chyme is too acidic or too fatty, it sends inhibitory signals back to the stomach. This is called the reverse enterogastric reflex.
It's the intestine yelling, slow down, I'm full, back at the stomach.
That's a perfect way to describe it. Plus, the presence of acid or fat in the upper small intestine causes the intestinal wall to release several inhibitory hormones: secretin, GIP, VIP, and somatostatin. These all travel back through the blood to the stomach to turn off the acid tap.
Okay, so the food, this chyme, is now an acidic, soupy, partially digested mess. It leaves the stomach and enters the small intestine, and immediately it gets hit by a flood of secretions from the pancreas.
The pancreas is this fascinating dual organ. Anatomically, it's very similar to the salivary glands. It has the acini, which produce the digestive enzymes, and a long system of ducts, which secrete a watery bicarbonate solution.
Let's look at the enzymes first. This seems like a really heavy arsenal of digestive weapons.
It is arguably the most important digestive gland in the entire body. For proteins, it secretes trypsin, chymotrypsin, and carboxypolypeptidase.
But again, safety first, right? These must be inactive.
Right. They're all secreted as inactive precursors: trypsinogen, chymotrypsinogen, and so on. They are only activated once they reach the intestine by an enzyme called enterokinase, which is secreted by the intestinal wall itself.
And the text makes a special note of something called a trypsin inhibitor.
This is a crucial failsafe. The very same cells that make the trypsinogen also make and store a substance that inhibits trypsin. This prevents any small amounts of trypsin from accidentally activating inside the pancreas and setting off a chain reaction that would digest the organ itself.
And if that inhibitor system fails,
You get acute pancreatitis. The pancreas literally starts to digest itself. It is exquisitely painful and can often be lethal.
that is incredibly high stakes. What about carbs and fats?
For carbohydrates, there's pancreatic amylase, which picks up where salivary amylase left off. And for fats, you have a whole suite: pancreatic lipase, cholesterol esterase, and phospholipase. This is the main place where the serious digestion of fats happens.
But for any of these enzymes to work, we have a major problem. The chyme coming from the stomach has a pH of, what, 1.0 or 2.0? And these enzymes need a neutral or slightly alkaline environment.
And that is where the second, equally important function of the pancreas comes in: the ducts. The cells lining the pancreatic ducts secrete massive amounts of sodium bicarbonate.
Baking soda, basically.
Chemically, yes. The mechanism involves carbon dioxide from the blood entering the duct cells, combining with water to form carbonic acid, which then dissociates, and the bicarbonate part is pumped into the duct lumen.
And the result of all that, bicarbonate.
You get a pancreatic juice with a pH of roughly 8.0. It's quite alkaline.
So it's the ultimate antacid.
Exactly. When this alkaline pancreatic juice hits the acidic stomach chyme in the duodenum, it neutralizes it completely. The text notes that there is literally a chemical reaction that produces carbon dioxide gas, and the result is a neutral salt solution, creating the perfect pH environment for all those pancreatic enzymes to get to work.
And the regulation of the pancreas is split, too. It's not one signal for everything.
It's beautifully split. Two hormones, acetylcholine from nerves and CCK, or cholecystokinin from the intestine, primarily stimulate the acini to produce and secrete the enzymes. But they don't cause much water flow, so the enzymes just sort of sit there in a concentrated sludge.
They need a flush to wash them into the intestine.
Enter secretin. Secretin is another hormone, and it's released by the duodenal wall specifically when it senses acid. Its main job is to stimulate the pancreatic ducts to produce that massive volume of water and bicarbonate solution.
So let me get this straight. Acid from the stomach triggers the release of secretin. Secretin tells the pancreas to release bicarbonate, and the bicarbonate then kills the acid.
It's nature's antacid, a perfect negative feedback loop to protect the intestine.
I love that. Okay, working alongside the pancreas, we have the liver and the gallbladder. They are secreting bile.
And bile is very interesting because, unlike all the other secretions we've talked about, it contains almost no digestive enzymes.
Wait, really? I always thought that bile digested fat.
It aids in fat digestion, but not by breaking chemical bonds like an enzyme does. It acts more like a detergent.
Emulsification.
Correct. Bile contains bile salts, which have a detergent action. They break the large globules of fat in your food into tiny microscopic particles. This dramatically increases the surface area so that the pancreatic lipase enzyme can actually get in and chemically attack the fat molecules.
And it also helps with absorption, right?
Yes. This is its second critical role. Bile salts form these tiny complexes called micelles with the final digested fats. These micelles act like little ferries that transport the fatty acids to the intestinal wall to be absorbed. The text states that without bile salts, you would lose up to 40% of your ingested fats in your feces.
That's a huge loss of metabolic fuel.
A massive loss. But bile has a second major function beyond digestion, excretion. It's the body's primary way of getting rid of certain waste products, specifically bilirubin, which is a breakdown product of old red blood cells, and excess cholesterol.
Now let's talk about the anatomy. The liver makes the bile, but it's the gallbladder that holds it.
Right. The liver secretes bile continuously, about 600 to 1,000 milliliters every day. But we don't eat continuously. So most of this bile is diverted into the gallbladder for storage between meals.
But the gallbladder is tiny. The text says it only holds about 30 to 60 milliliters. How does 1,000 milliliters of bile fit into a 60 milliliter bag?
Concentration. The lining of the gallbladder actively sucks water, sodium, chloride, and other small electrolytes out of the bile and returns them to the blood, leaving the bile salts, cholesterol, and bilirubin behind. It concentrates the bile, on average, about 5-fold, but can go as high as 20-fold.
So it's like making a bile concentrate, like espresso bile.
That's a great analogy. But this concentration process comes with a significant risk. If you have too much cholesterol in your diet and not enough bile salts to keep it dissolved, or if there's inflammation in the gallbladder, that cholesterol can precipitate out of this super concentrated solution.
And form gallstones.
Gallstones. They are essentially little rocks of precipitated cholesterol that form inside this concentrating tank.
So when do we decide to empty the tank? What's the trigger?
The primary trigger is the presence of fatty food entering the duodenum. This causes the intestinal wall to release the hormone CCK.
The same hormone that triggered the pancreatic enzymes.
The very same one. CCK is a multitasker. It travels in the blood to the gallbladder and causes its muscular wall to contract rhythmically. At the very same time, it causes the relaxation of the sphincter of Oddi, which is the little muscular gatekeeper that controls the opening into the intestine.
So the gate opens, the tank squeezes, and this jet of concentrated detergent floods the intestine to mix with the incoming fat.
It's all about precision timing.
Now, probably the coolest statistic in this entire chapter for me was the recycling program. The text calls it the enterohepatic circulation of bile salts.
It is the ultimate recycling program. The body works very hard to make those bile salts from cholesterol, and it does not want to lose them. So when they've done their job and they reach the end of the small intestine, the ileum, about 94% of them are actively reabsorbed into the blood.
94%.
They travel back to the liver through the portal blood. And the liver cells, the hepatocytes, grab them out of the blood and resecrete them back into the bile.
How many times does a single molecule of bile salt do this loop?
The source material estimates that, on average, a bile salt molecule recirculates about 17 times before it is finally lost in the feces.
17 times. That is just incredible efficiency.
It is. It means the liver only has to synthesize a tiny amount of new bile salts each day to replace that small 6% that is lost.
Okay, we are in the home stretch of our tour, the intestines themselves.
The small intestine has its own very important secretions, of course.
Yeah.
Right at the beginning, in the duodenum, you have a special set of glands called Brunner's glands.
What do?
They secrete a very thick alkaline mucus, and again, you can guess the reason: protection. This is the very first spot that the brutally acidic chyme from the stomach hits. This mucus is the first line of defense.
And the text mentions a really interesting link to stress here.
Yes. Brunner's glands are strongly inhibited by sympathetic stimulation. That's the fight or flight stress response.
So being stressed literally turns off this protective mucus layer.
Exactly. And the text points out that if you are chronically stressed, you stop producing this protective mucus, leaving the duodenal bulb vulnerable and exposed to the full force of the stomach acid. This is one of the key reasons why psychological stress is a major factor in the formation of peptic ulcers.
That makes total logical sense now. Okay, what about further down in the crypts of Lieberkühn that we mentioned earlier?
Here, you have cells called enterocytes that are producing a very large volume of watery fluid, about 1,800 milliliters a day. But this secretion is different from the others. It's a carrier fluid.
A carrier fluid, what does that mean?
The crypts, which are down in the valleys, secrete the water and electrolytes. This fluid flows out of the crypts and is almost immediately reabsorbed by the adjacent villi, which are the finger-like projections. It acts as a watery vehicle to dissolve the nutrients from the chyme and carry them onto the surface of the villi where they can be absorbed.
So it's like a constant circulating conveyor belt made of water.
Precisely. It brings the nutrients to the absorptive surfaces.
What about digestive enzymes in the small intestine?
This is a very common misconception. The actual secretion of the small intestine, that watery fluid, has almost no enzymes in it.
Really? But I thought all the final digestion happened here.
It does, but the enzymes are not floating around free in the fluid. They are embedded on the surface of the epithelial cells themselves, on what we call the brush border.
So the food has to physically touch the wall of the intestine to be finally digested.
Yes. You have peptidases to break down the last little bits of protein. You have sucrase, maltase, isomaltase, and lactase to break down sugars. And you have intestinal lipase for fats. They are all fixed in place on the cell membrane, ready to act on any nutrient that comes into contact with them.
And finally, the last stop, the large intestine, the colon.
Here, the chemistry simplifies dramatically. No enzymes at all, just mucus.
Mucus, mucus, and more mucus.
The colon has many crypts, but they contain almost exclusively goblet cells that produce mucus. This mucus protects the colon wall from excoriation by the hardening feces, and it provides a barrier against the huge amount of bacterial activity happening in there. It also acts as an adhesive, a glue, to hold the fecal matter together.
And it also creates a barrier against the acids that all those bacteria are producing.
Yes. The mucus is alkaline. It contains a lot of bicarbonate, specifically to neutralize those bacterial acids and protect the colon wall.
And what happens if something irritates the colon, like a bad infection?
A condition called enteritis. The mucosa responds by secreting massive amounts of water and mucus, far more than can be reabsorbed.
In other words, diarrhea.
It's a flushing mechanism. It's a protective reflex. The body is trying to dilute and wash away the irritant as fast as possible. It results in dangerous fluid and electrolyte loss for us, but it's a fundamental survival reflex for the gut itself.
Wow. What a journey. We started with this mind-boggling number, 6.7 liters of potential fluid, and we've tracked it through acid baths, enzymatic explosions, detergent mixing, and these incredible recycling loops.
It is a chemical masterpiece running on autopilot.
To summarize for everyone, let's just quickly look at the journey again. First, in the mouth, you've got this hypotonic saliva for taste with antibacterial agents and the beginning of starch digestion.
Then the stomach, a pH 0.8 acid bath created by that crazy proton pump. Its job is to kill bacteria and activate pepsin to start dissolving meat.
Then the pancreas swoops in as the great neutralizer. It sends in bicarbonate to fix the pH, and then a bomb squad of enzymes to digest everything: fats, proteins, and carbs.
Alongside that, the liver and gallbladder provide the detergent-concentrated bile stored and timed perfectly, and then recycled with 94% efficiency.
Then the intestine provides a water conveyor belt and what you call contact digestion with the enzymes on its walls.
And finally, the colon. Just pure mucus for lubrication, for binding, and for protection.
And I think the final aha moment from this chapter is the balance of it all. The body creates and carries around substances that can dissolve meat and destroy cells, yet it contains them safely using these brilliant strategies like inactive precursors, like the pepsinogen, and these constant physical and chemical barriers like mucus. It is such a precarious dynamic equilibrium.
It really, really is.
So, here is a provocative thought to leave you with. We talked about how incredibly efficient the body is, recycling bile salts 17 times, using the gallbladder to store and concentrate bile because we eat in distinct meals, not continuously. But in modern medicine, we often surgically remove the gallbladder, a cholecystectomy, or we perform surgeries that bypass large sections of the gut for weight loss.
That's an excellent point to bring up.
If you remove the storage tank, the gallbladder, but the liver keeps pumping out dilute bile 24/7, what happens to that beautifully timed, concentrated detergent blast that's supposed to meet a fatty meal? How does that entire factory adapt when you suddenly remove a key warehouse? Does the rest of the gut change its chemistry to compensate?
That is a question worth chewing on.
Indeed. So, the next time you sit down for a meal, just take a second to appreciate the silent, incredibly complex, high-stakes chemical industry that is powering up inside you. Thanks for listening to The Deep Dive.
Stay curious.